that was my actually latest slide edit that I ever did. I forgot to fix the front page. So before I get started, basically, we have the Reba Kickstarter. You have heard about it, maybe. We have it still going, so you can still fund it. So there's the QR code. But if you didn't take the opportunity to scan it now, you need to ask me later. So hardware-wise, no, I would say that's where we started, but that's not true because it's already called GRiSP 2. But let's not talk about GRiSP 1 anymore. It was an experiment that failed, and we make GRiSP 2 very quickly to fix it. So this is like the size is IMX6ULL. That's an NXP system on a chip, which is large enough to run Linux. We have enough memory to run Linux, so it actually runs nerves. It's an officially supported nerves board. But what we actually care about is to run. No, actually not. We care about all kinds of things nowadays. But what we want to look at today is kind of like running the Beam directly on hardware. And we have heard about AtomVM, and there was amazing progress, so really kudos to the AtomVM people. So they do the bottom-up approach, and I'm showing you the top-down approach. So starting with all of OTP, and then getting it into smaller corners. So that's kind of like the map. GRiSP 2 is like somewhere in the middle, in the three-dimensional space, like power, speed, size, and cost. And we wanted to get, I want to see how close I can get to the origin, while still being able to run all of OTP, basically, and the normal Beam, the vanilla Beam. So power-wise, Raspberry Pi is like a normal Raspberry Pi, not like these little Pico devices. Normal Raspberry Pi is off the charts, somewhere over the screen over here. GRiSP 2 is kind of like, it's pretty powerful. It is nice. It's in a nice middle thing, and we wanted to get very close to the origin. And because the funding was coming from an energy harvesting EU project, I optimized for power most, basically. So power consumption is also what half of the talk is about today. So we made this hardware. It's an STM32. It is a version of it that is supporting external memory and is very power. It has a lot of like power switch off modes, and it's very interesting for power conserving things. We planned for a 32 megabyte external low power RAM. It has also 3 megabytes of internal RAM, 4 megabytes of flash. We stick the bootloader in there at the moment. It has an SD card slot, and it also has a really big variety of like power modes, wake up things, and that is the stuff that we will be playing the next months, basically. So this is like work in progress. It's not done yet, but we're making good progress. And it has an USB host client, so it's called on the go. So basically, it's a USB interface. You can switch to host or client. So basically, the board can be a client, and then you can let it play Ethernet or something, and then plug it into your laptop and have like a network connection running immediately. It has another USB for the console. That's the one that I wired up here on my setup. And we got 4 of these PMOD connectors that we also use in GRiSP 2, where you can stick in these little modules with sensors and actuators. And the plan is to run a vanilla Erlang runtime. Very low power during run mode, and it has a high power saving. I will say that. And the important thing is RAM chips. You need to have really power conserving RAM chips because the RAM uses a lot of power. So that's, for example, a thing that's not optimized in GRiSP 2. We have just normal RAM. The RAM is not available. It's only available in 16 megabytes in the form factor, so we kind of like suddenly got only half the RAM that we planned. Yeah, that will be fine. Well, we'll see. So that's how it looks. I have one here. If you want to have a look afterwards, it's over here. So that's the 4 PMO connectors. The green connector on the top lower corner, that is for the energy harvesting device. So it has 3 pins. It basically has like the 5-volt pin that it switches on and off. And it has also a pin that lets us measure how charged the capacitor in the energy harvesting devices. So they were making energy harvesting devices with temperature gradient, so you can heat one side and cool the other side, and then it produces energy. And the plan was to run off this energy, which kind of like allows a single-digit milliwatt of power consumption on the average. There's also a little battery thing in the corner, which is not placed here because we have a real-time clock, which is very important if you want to sleep for 5 minutes and then wake up and have nothing running except the little clock. And SD card slot on the top. Yeah, that's about it. I think you've seen enough. So there we got started with the thing and actually starting Beam, and then here it's basically we're running out of memory here. Cannot allocate memory of type binary. Basically after the binary, like the binary image, that was really the starting point. We had only 7.5 megabyte free of the 16, and we only got 7 modules in. So that was like, ooh, this will be hard. But in the end, after this longish journey with many slides here, that I don't bore you with because I showed them in Stockholm, and the video is already out, so I actually cut all this out. And if you want to watch the video, that's the QR code leading to YouTube too, so you can watch the video. So there was an elongated journey, basically getting more and more stuff in until we finally actually got to the shell. Unfortunately, 3 days after the conference in Stockholm. In the conference in Stockholm, we almost only got to the shell. And it is basically all of kernel and standardlib that's booting, except we fixed the Unicode module. So our Unicode, because Unicode module is huge, that was the last module we couldn't get in. And we fixed it by, oh, let's assume Unicode is always ASCII, which is okay for a device of this size. What do you need? Whatever. I don't need emoji on this device, I hope. So the thing we are currently working on, which is also important for the power saving to achieve that, is we want to use the internal RAM. So because we kind of like we got everything booted in the external RAM, and that's also what I will demo afterwards. But the internal RAM, the 3 megabytes, is we put a few stacks in there, stuff like that, but we are not really using it. And in the journey, basically getting the image smaller to get more Beam files in, we actually achieved to get it smaller than 3 megabytes. So we basically what we have is we have the Beam, the Erlang runtime, a TCP stack, the rest of RTEMs basically for threads and all this hard real-time stuff. Smaller than 3 megabytes, basically, in the end. And the TCP stack is a full-blown TCP stack, like with IPv6 and everything. So it's it's a FreeBSD TCP stack, which is quite bulky. But it has all the features that you could dream of. So if you can move the code into the internal RAM, we can use all the 16 megabytes for Beam files and heaps and stuff like that. And so that would give us just like 3 megabyte more memory. But we are not quite there yet. So before the conference, we were like, oh, it's almost running, but it's crashing over there. There was a lot of like very low-level fun things, like, oh, you load it into internal RAM until you finally manage that, and then because first you can't even write it, and then you jump to it, and then it crashes immediately. You get some alignment, assembler alignment problems, and then you need to switch off some memory protection bits. So it doesn't have an MMU. It's much too small, but it has like area memory protection stuff that can get in your way. So it was a struggle, but we basically, probably 3 days after the conference, we will be there again. So let's talk about power. So if you actually have, I mean, one question I very often get is like, how much power does your GRiSP board use? Like, it depends what you do on it. If you do a lot, then it takes more power. If you do a little, so software is a very big factor of the power consumption. And that's why we need to look at the power consumption and then tweak the software to actually make it fix. Of course, you also need hardware features for that. So what you see here is like the timeline on the right. So that's just running time in some arbitrary scale. And to the top is power or current draw or whatever. Since usually the voltage is constant, it's all proportional. And what you normally see when you see a running system, an embedded system, you see a baseline power draw. So that's always running, no matter what you do, even if you sleep. And then you have like these spikes, like these boxes where you do stuff. Usually an interrupt happens and you want to calculate stuff or something happens. And depending on what you're doing, it's more irregular, and it can be also looking like imagine this thing fractally put into itself again and again, so small spikes in between the larger spikes for other things. And so it is more complicated in reality, but it all boils down to that, and you need to optimize that. And how do you optimize that? So what's very important is you want to lower the baseline. That's very important, and lower the baseline means put the CPU in very deep sleep, like switch it really off. Switch off all the hardware. Switch off the RAM. So we have a RAM that can be put in a very low power mode. That is the important thing. And that's also kind of like it. That is much easier if you run from internal RAM, by the way. So that's why we want the internal RAM, because if I'm running from the RAM and I'm switching off the RAM I'm running for, I need to kind of like do all kinds of like shenanigans to actually get this done, because you need to jump somebody. You cannot run in the RAM that you're switching off. Code needs to be, at least the switch off code needs to be somewhere else. And if all the code is somewhere else, then we can switch off the RAM very easily. On GRiSP, we can also switch off all the power to all the PMODs. So we can switch the PMODs on and off, PMOD by PMOD. So that is a feature that GRiSP 2 doesn't have. Because of course the PMOD, the sensors also use power. And if you're not measuring anything, you don't need to power the sensor. You wake up and you make a measurement. That's the usual IoT thing. You wake up, you make a measurement, you send it over the network, and then you sleep again. So we reduced the baseline, we optimized all the things in the hardware that we can actually do. What's next? Well, some people would say, yeah, actually in the CPU you can reduce the clock speed, and then it uses less power. Don't do that. That's almost always wrong. Like 99%. Because what happens, if you see what happens with the boxes, they kind of like get lower, like by half, but they get wider by much more longer. Because you have to imagine, like in the CPU when it's running, there is a lot of transistors kind of like being powered. And every little transistor on the chip has a leakage current. So it leaks current all the time, as long as it's powered. And if you're running slowly, then you still have all the leakage power over all the time. And what you actually want to do is you want to kind of like run very quickly and then sleep again very deeply. Race to the sleep, basically. That is the way to conserve power in embedded systems. So you want that to look like that. You want to, I mean, that is the thing that we all do when we optimize our systems, like classic system optimization. So you benchmark your code and make sure that it's not running long, and maybe replace something very time-consuming with an if or whatever. So you make it run faster, basically. So that is the thing I don't need to explain to you. And then when it runs faster, then you can sleep longer. And because you reduce the baseline, then that's what you get, basically. So your total energy that you need is the surface under this curve, basically. So that's where we get, basically. You want to reduce the surface area. And what you can do also is, of course, run less often. That is usually in the last tweak. Like, you did everything, you optimized everything, then you kind of like get your battery or whatever power device, and you say, oh, that was okay, we're not quite there yet. Maybe we don't need to measure the temperature every 10 seconds. It doesn't change that often. Maybe you just measure it every minute. And that's what I'm doing here, run less often, sleep more. So that is kind of like the 101 of power reduction. So the problem is you also need to kind of like see what you're doing, because we don't know how much power this thing takes. And of course you can do the tweaks anyway, like you say, okay, let's optimize the code, let's run less often, let's switch off all the bits. But then you always have, like, if you then actually look at the power consumption, suddenly you find like hidden things. Like, what is actually running every millisecond here? Who is that? And then you need to figure out who that is. And for that, you need to measure. And for measurement, that is actually part of the demo. You need some device that actually measures. And the device that I have here, it's called Joulescope, was actually, it's actually a friend of Frank actually recommended that to me, from like Frank Kunlet from the NERVS project, because it's a friend of him kind of like made this on a Kickstarter. And it's a really nice device, I like it. So measuring the current is actually not so easy. Measuring voltages is much easier because you have like some high impedance input and you measure the voltage, and that's what an analog digital converter does. It measures the voltage usually. If some of you that have tinkered with hardware remember the old kind of like multimeter things where you had like the current things, you had like a whole range of current settings like amperes, milliamperes, or like 100 milliamperes, 10 milliamperes, microamperes. And you need to be very careful what to switch on because either you fry your resistor or nothing works because the resistor is too big in the device. Because what you do when you measure current is you let the current flow, and you need to interject yourself in the current because the voltage you can just measure from the outside, basically. It's a potential, it's the height. But if you want to kind of like measure the water flow, you need to inject yourself into the water flow somehow. And you do that by inserting a resistor. And the resistor is also reducing the current, basically. So it's kind of like hindering the current. But what you actually want to achieve is that the voltage drops over a resistor, basically from one end to the other end on a resistor, and the voltage drops. So there's a potential on the resistor that you can then measure as a voltage again. And that is kind of like Ohm's law. I think some of you might remember still. It's one of the most simple electric laws, basically. So the voltage basically is proportional to the resistor and the current, basically. But kind of like if your resistor is too small, you're not getting any voltage when there's only little current flowing. You don't see anything. It's like tiny. And if you make it larger, then when more current flows, a lot of voltage drops. And then on top of that, the ranges of current that you want to measure in hardware is going from amperes, like full amperes, or at least a few hundred milliamperes, down to micro and nano amperes if you really want to conserve power. So you have like several orders of magnitude to measure, and you want to measure it very quickly because you want to watch your software running and see how much power it draws. So what you need is a device that has basically this multimeter in there with a little switch, but it can turn the switch very quickly. So it's going up and down all the time and finding the right range for what you want to measure. And so this device does this in the megahertz range. I forgot the actual spec. I just got it. I just started playing with it, basically. And that is not easy. So it's not totally cheap. So let's talk about the setup here, basically. What we're measuring here, so that is the perfect measurement, basically, that you can do is you measure the voltage and you measure the current. So for the current, you need to inject the device. So between the yellow and the red with the eye is basically the resistor inside the box. And you also want to measure the voltage separately on the box. And ideally, you want to measure both the voltage, like the current, it doesn't matter where you measure it, where you put it in the cable, but the voltage you want to measure close to the device and directly lead it to the voltage pins. Because the voltage changes over the cable has a resistance too and all kinds of things. In our case, we went with a simplified thing. So that's another setup, basically say, yeah, I don't care so much about the voltage. It's kind of like constant anyway. It's not so important. Then you just like use the same cable, basically. So I have that's the 3 wires that you see here, the yellow, the red, and the black. So that's what we wired up. That's how it looks. So you can see it. That's what I have here. I took the picture just before. Oh, there's a little paper tab from the USB cable that I opened. I just took the picture before in my hotel room when I tested the setup, basically. So yeah, there's the Joulescope, these wires. So I basically, in this case, I made a USB cable which actually hooks into that. That was a lot of like late night soldering, like cutting it open very thinly and then pulling out the little wires and cut one of the little wires only, the current wire, keep the other ones running because I want the data also intact because this is the wire that powers the device and it's also having our USB console. And I want to see the console because otherwise the demo would be kind of like not so interesting. Yeah, so yeah, that worked. But So for the Joulescope, you also can get like front plates. If you do measurements a lot in a certain thing, like USB, then you just swap the front plate here, and then you have a USB plug, so you can inject that. So that's, but I didn't have that. So I need to do the little soldering inside this yellow thing. There's a lot of stuff in there. Yeah, I think I talked long enough about the demo. Let's demo. So let's put this in play. So this is the scope, basically. We see, so the numbers are not very readable here. So it's not doing anything because I switched off the power, basically. And because we also want to see what's happening, here's our console, which is disconnected at the moment. So it says, the thing in the bottom, it says a little bit, oh, actually, I can make this larger. Oh, no. I shouldn't have done that. And then make the console smaller again, because we want to see the thing. So now it's a bit more readable, I hope. So yeah, it's disconnected. It's not doing anything. So let's switch it on. So currently you see that nothing's happening, but what you see maybe, I hope it's visible on screen, there's this one spike here in the beginning. And if you look on the number here, this is 7 amperes. What is going on? Well, that's the inrush current. You switch something on, you have capacitors on, and the current needs to charge all the capacitors. And that's actually quite a lot. And we're not seeing what's going on down here, because it scales to it is an auto scale, so we only see the 7 amperes. So you see it wobbles a little bit on the bottom. So we need to wait until the peak goes away, so to see more stuff. So when it goes away, it actually will scale up. So just about now. So now we see what's actually going on. So this is still booting. So it's, no, it only says connected, and it's not saying anything else. What's happening? That does not look good. But it's actually doing something. Why I'm not seeing anything? Let's try again. I think my serial line is broken. But it says connected. Disconnected. Demo gods. Okay, let's switch on the power again. And then it goes away. Why does it do it? Okay. It's powered. So this worked on the hotel room just a few minutes ago. It's supposed to show me stuff here. Okay. Let's start the serial thing again. So that is our GRiSP board open. Push the little reset button. That's better. Okay, that's what I wanted to see. So maybe I messed it up by scaling it up, but I still try to scale it up. So yeah. So basically starting Beam, and it's trying to go into Erlang shell mode. And what you see here is basically the booting process. So there was a weird spike here. I don't know what that is. We need to get the spike out of the way. You see little wobbles here. That's basically the Beam files it's loading. So this is taking some time because it's loading a lot of Beam files, and it's not a fast CPU. Now we see more. So I didn't kind of like look at that, because when you really want to measure your software, what this box also has, it has little input pins where you just have a logic level. So you put the GPIO on that, and then in your software you switch on the pin on and off, and so you figure out like what's causing what, and you play around with that, and you do forensics basically. And we will dig into later on when it's actually booted. We will dig into the details. Let me see how much time do we have. Yeah, we're still good. So yeah, the booting takes some time, and so my assumption is that the peaks here, that's kind of like the loading from the SD card, like another file, and the other thing is the loader basically doing, because it's actually calculating something. Because that is like, this is the loading, the baseline loading is in the order of 40 milliamperes. That is reasonable for the thing is computing. And the other thing is more, so it's probably doing something else and powering the SD card. That's my current baseline assumption. As I said, I just got the box. I will have more explanations in my next talk. Then I will pick out all the peaks here and say, tell you that this is peak Zugspitze and this is peak. So any moment here, it takes 1.5 minutes to boot. And so let me talk about booting. So if you run off a battery, so that was a large file, by the way. Do you see that? That one here? See, it's longer. So it's different things are happening. So the booting is actually a thing that often, like hardware that runs on energy harvesting, doesn't have a problem with, because usually you run from Flash, you have just a little program that you switch on and it runs off. And there's no concept of booting. But yeah, if you want to have Erlang, we need to boot somehow. And so for the energy harvesting device, here's my shell. So just to prove that it's actually alive, 1 + 1 is 2 still. So it's actually working, and we also are supposed to see now lower energy. So I take away the shell for a moment so we see more. So that's actually the thing in run mode. That's what it does when it's running. And let's stop that for a moment so we can actually zoom in a bit. Oh no, let's do a little experiment on the shell. So let's do a bit of compute. I mean, this was probably my 1 + 1. Let's say, let's make a list of 10,000 elements. Last time I did that, I had enough memory for that. So yeah, it made a list. And we see that's where it made the list. That's what it did, basically. It did compute. So let's stop that and dig in. Pause. And let's kind of like first look at the current here. So the current here, when it is computing, is 40 milliamps. So that is probably my baseline assumption that it's computing when it's loading. The baseline, let's zoom into that. Oh, I want to see the little peak here. So the baseline is currently 50 milliamps. So there's a way to go to single digit. So I want this to be at maximum 5, 4, 7. I don't know where we can get. The hardware guy said, yeah, we will try. Okay, we will see. And then now let's dig into that, because you see, if you look at that, there's these kind of like regular spikes here. And if I mark that, that's too small for me to see. Dual markers. So I actually move the markers here. So that's happening every. So very small numbers here. Where do I see the time? So that is happening every 500 milliseconds. That is probably not Artemis doing something. It's probably Erlang doing something every 500 milliseconds. I guess it's the Erlang scheduler running. I don't know. I didn't dig into it. I told you, there's forensics happening. But as I said, you see this like fractally, wheels within wheels. So this is the big thing. And if I zoom in, then I see there's little spikes here. Oh, what are those? Okay. Oh, how long are those? And what you also see, it looks a bit wavy. The wavy thing is not a real thing. This is kind of like the sampling frequency of the device, basically interfering with the sampling with the actual signal, basically. And if you look at that, I can go in further. And then I need to. Oh no, I messed it up. Can't see my. Oh, I can do multiple markers. A new feature discovered. If I measure that, oh, it's 1 millisecond, very precisely. What's going on there? Well, this is the timer tick of Artemis, which is still at 1 millisecond, which is much too fast for energy harvesting. So that is one of the tweaks, like, yeah, okay, let's set this to 100 milliseconds, because you don't need very precise timer ticks, so normally in a system, if you want to be very performant, you want fast timer ticks, but you don't want that. And we can still see the baseline is 50 milliamps. And so this kind of like, if you really want to know, then you see, so that is then, now that is analog electronics happening, stuff like inrush current, and that's how this little spike, that's a timer tick, basically. It's a little piece of assembler code that just ticks the timer. Okay, I think that is all I can show you for now. Let's continue with the slides a bit, but I think I'm already at the end. How much do I have? 5 more minutes? Yeah, that's perfect. Play. So that was the demo. For the energy harvest, I started talking about the energy harvest, then it was done booting. For the energy harvesting, if you kind of like have a thing that needs to charge as a capacity by some kind of like very tiny current, and then you have a certain charge, when you boot, then either you need to fit the whole boot into one charge, or you need to boot intermittently. So I already have plans to kind of like inject into the boot script, like every so-and-so files, like, are we having enough charge still? Oh yeah, okay, let's load another one. And then, oh, no, not. Let's sleep until the charge is enough. But we need to know how the charge is enough. And that's why we need these 3 pins, because we need to measure the charge. And that's the measurement logic. So we put on kind of like a variety of measurement logic, so you don't need to read all that. You can read it afterwards, basically. I explain the most things. So we have an analog digital converter to measure the voltage, but that actually might pull too much power, because well, you need power to measure, basically. But that is an experiment. If it's a battery, then it's probably fine. And then we have another way, basically, is we have a way that is this triangle here is basically a comparator, the triangle that's pointing to the right. So you have basically the voltage you want to measure, and then you have a comparison voltage. And this is then a logic signal, basically. And you do a digital analog converter, which uses less power to create the signal, and we have a bunch of like fixed signal sizes, if you even don't want to do that. And this comparator can also be used for a wake-up interrupt. So we can basically set this whole thing up in a way that, okay, we don't have enough power, wake me up when we have enough power, for a definition of enough power. So that is the thing we can do while booting. If you're booting off a battery, which is often the case, this doesn't care. The battery, I mean, when you start, you only boot once. When you put in a new battery, then you boot and you keep running forever. Hey, we're using Erlang. We are building systems that run forever, so we don't need to care about like booting again. That's a small topic, basically. The thing that we are running on this GRiSP, I kind of like need to introduce the new names, because before we had the GRiSP stack, that was the Beam on RTEMs running directly on hardware. That has a new name now. It's called GRiSP Metal, because we have other stacks now. Because our customers have different needs, and some customers want the Linux because you need a Linux driver for something. And yes, they can use nerves, but they can also use GRiSP Allo now. And we make the stacks in a way that on the Erlang and Elixir level, they basically look almost the same, so you can swap them out underneath and run the same drivers and code and whatever. So GRiSP Allo is basically similar to nerves. It is running on Build Road Linux. It has a bunch of extra features. It can run multiple Erlang VMs. You can actually pin it to cores, and you can use real-time Linux features. We are into real-time. And run the different VMs on different priorities. So you can have like a critical VM and the thing for the user interface. So that's Alloy. And then if you look into industry, many companies want to use Yocto instead of Buildroot, because they already have a Yocto setup and all their devices are done with Yocto. So we will provide the same thing with Yocto as soon as somebody wants it. So we are playing with it. So we have a prototype. We are ready to go. And then if anybody basically says, okay, here's a coin, throw the coin in, then they will get it with Yocto, basically. So what I saw today, actually from the Atom VM people, that impressed me a lot. So really, they made a lot of progress. And maybe there's another size that is necessary. Maybe. Where's my animation? Ah, there. Ah, what is doing? Don't do that. Yeah, I double-clicked. So maybe we need a GRiSP atom based on Atom VM. I don't know. What do you think? Let's talk. Because then we can go even smaller. Because what we actually want to build, the thing we actually want to build is not just like making these stacks, that there's a reason for that. We want to build a compute continuum from the cloud, edge, to IoT fog, as broad as possible. And the continuum is a little bit kind of like a misnomer, because we actually want to focus on kind of like things when the network is not continuously running, like intermittent running, bad connection, things that are on and off again, a laptop that is carried from here to there and carries some data, all kinds of things. So it's a discontinuous continuum we want to build. So for that, we want to run the same Beam files everywhere, ideally. And I think with Atom we can do so now. So this continuum that we are building is basically then, that is the thing we want to, in the future, want to make money with it, but there's a lot of free stuff. If you have a GRiSP board, you can actually get some free stuff. You can do remote software update already. Basically, same thing like Nerves Hub. We're just starting, but we make some progress there. And no, one more click. No? Two more clicks. No. So GRiSP Nano is almost done, the project. So we are ready to make the hardware. We need to test a few more subsystems. So we will start a Kickstarter soon. We didn't make it before the conference. This was my initial plan. But the thing is, Kickstarter doesn't let you run two Kickstarters. So we had the Rebar Kickstarter still kind of like open, and we didn't ship the T-shirts yet. And they basically said, you ship your old stuff first, and then you start a new Kickstarter, which I can totally understand. So this basically leads to a page where you can basically type in your email address, and we send you an email when the Kickstarter opens. I hope in December, but yeah.